Earth's axial tilt stands as one of the most fundamental astronomical factors influencing our planet's climate, seasons, and habitability. This 23.44-degree inclination between Earth's rotational axis and its orbital plane creates the rhythmic dance of seasons that has influenced all life on our planet. The remarkable stability of this tilt, maintained within a narrow range over millions of years, has allowed complex life to evolve and thrive across Earth's diverse environments. This analysis explores the science, history, variations, and wide-ranging effects of Earth's axial tilt, providing a detailed examination of this crucial planetary characteristic that shapes our world in countless ways. Axial tilt, known scientifically as obliquity, represents the angle between an object's rotational axis and its orbital axis. In Earth's case, this is the angle between the imaginary line passing through both the North and South poles and the line perpendicular to Earth's orbital plane around the Sun. This definition distinguishes axial tilt from orbital inclination, which is a different astronomical parameter. Earth currently maintains an axial tilt of approximately 23.44 degrees, creating a significant deviation from perpendicular that produces profound effects across our planet. At an obliquity of 0 degrees, a planet's rotational and orbital axes would align perfectly, with the equator precisely matching the orbital plane. But Earth's substantial tilt creates the conditions necessary for our familiar seasonal patterns. The scientific terminology describing Earth's tilt provides important precision in astronomical discussions. Astronomers refer to Earth's tilt specifically as the obliquity of the ecliptic, referring to the angle between the ecliptic and the celestial equator projected onto the celestial sphere. This angle is commonly denoted by the Greek letter epsilon in astronomical calculations and literature. When visualizing Earth's axial tilt, imagine the planet's axis remaining pointed in roughly the same direction in space throughout its yearly orbit, with this consistent orientation causing one hemisphere to receive more direct sunlight than the other at different points in the orbital path. This persistent directionality of Earth's axis, combined with its orbital motion, creates the fundamental mechanism driving seasonal changes across our planet. The fixed orientation of Earth's rotational axis relative to the background stars means that as Earth orbits the Sun, the northern hemisphere points toward the Sun during one part of the orbit and away during another part, with the southern hemisphere experiencing the opposite pattern. When the North Pole tilts toward the Sun, the northern hemisphere experiences summer while the southern hemisphere experiences winter, with this relationship reversing 6 months later when the South Pole tilts sunward. This basic mechanism represents the primary driver of Earth's seasonal cycle, far more influential than the minor variations in Earth-Sun distance throughout the year. The consistency of this tilt, maintained within a narrow range over geological timescales, has provided the stability necessary for Earth's complex ecosystems to develop and thrive. The measurement and definition of axial tilt involves specific astronomical standards and conventions. The International Astronomical Union has established 2 standard methods for specifying a planet's tilt. The first method bases measurement on the planet's north pole, defined in relation to Earth's north pole direction. The second method uses the right-hand rule to define a positive pole for determining orientation. These standardized approaches ensure consistent measurement and comparison of axial tilt across different celestial bodies in our solar system and beyond. When measuring Earth's axial tilt specifically, astronomers calculate the angle between the ecliptic and the celestial equator, providing a precise value currently measured at approximately 23.44 degrees. The measurement precision for Earth's axial tilt has improved dramatically throughout history, from ancient approximations to modern values calculated to the arcsecond. Modern astronomical measurements can detect even subtle variations in Earth's orientation, allowing scientists to track the small but ongoing changes in our planet's axial tilt. These precise measurements reveal that Earth's axial tilt is not absolutely fixed, but changes very gradually over time. Currently, this tilt is decreasing at a rate of approximately 46.8 arcseconds per century, equivalent to about 0.8 degrees every 100 years. This gradual change reflects the complex gravitational interactions between Earth and other bodies in our solar system, particularly the Moon, Sun, and larger planets, which exert subtle but persistent influences on our planet's orientation. The recognition and measurement of Earth's axial tilt has a rich history spanning millennia, reflecting humanity's evolving understanding of our planet's position in the cosmos. Ancient Greek astronomers made remarkably accurate measurements of Earth's obliquity as early as 350 BCE, when Pytheas of Marseille measured the shadow cast by a gnomon at the summer solstice. This early scientific approach demonstrated sophisticated astronomical knowledge well before the modern era. The pursuit of astronomical knowledge continued across civilizations, with the Caliph al-Ma'mun of Baghdad directing his astronomers to measure Earth's obliquity around 830 CE, producing results that were used throughout the Arab world for centuries afterward. This cross-cultural astronomical investigation highlights the universal importance placed on understanding Earth's orientation in space. Medieval astronomical understanding included a concept called trepidation of the equinoxes, a widely accepted belief that both precession and Earth's obliquity oscillated around a mean value with a period of 672 years. This theoretical framework attempted to explain observed celestial changes, but was based on incomplete understanding of Earth's actual astronomical behavior. The gradual refinement of astronomical knowledge eventually challenged this misconception. Ibn al-Shatir in the 14th century may have been the first scholar during historical times to recognize this theory was incorrect, while Fracastoro in 1538 became the first to realize that Earth's obliquity was actually decreasing at a relatively constant rate rather than oscillating. These intellectual breakthroughs represented important steps toward our modern understanding of Earth's dynamic, but gradually changing axial orientation. The early modern period brought increasingly precise measurements of Earth's axial tilt. Tycho Brahe, working in Denmark around 1584, likely produced the first truly accurate Western observations of Earth's obliquity using advanced astronomical instruments of the period. Other significant contributors to this knowledge included astronomers such as Althussi, Purbach, Regiomontanus, and Walther, whose collective work gradually built a more accurate understanding of Earth's orientation in space. By 1437, the astronomer Ulugh Beg had determined Earth's axial tilt as 23°30, 2350-47 degree, demonstrating the remarkable precision achieved even with pre-telescope astronomical tools. This historical progression of increasingly accurate measurements reveals humanity's persistent quest to understand our planet's fundamental astronomical parameters. Earth's axial tilt is not perfectly static, but undergoes cyclical variations over long timescales. Over a cycle averaging approximately 40,000 years, Earth's axial tilt oscillates between minimum and maximum values of 22.1 degrees and 24.5 degrees respectively. This 2.4-degree range of variation may seem modest, but it produces significant effects on Earth's climate patterns over geological timescales. These long-term variations in axial tilt form one component of the Milankovitch cycles, a set of cyclical changes in Earth's orbital parameters that collectively influence global climate patterns. The slow oscillation in Earth's tilt results primarily from gravitational interactions with other bodies in our solar system, particularly the Moon, Sun, and larger planets like Jupiter, which exert torques on Earth's equatorial bulge. In addition to the gradual change in the angle of tilt, Earth's axis also experiences a wobbling motion called precession. Similar to how a spinning top wobbles as it rotates, Earth's axis traces a circular path in space while maintaining its angle of tilt. This precessional motion completes one full cycle approximately every 26,000 years, gradually changing the direction in which Earth's axis points relative to the stars. Precession affects the timing of the seasons relative to Earth's orbital position, altering which hemisphere faces the Sun at perihelion versus aphelion. When one hemisphere faces the Sun at perihelion, it experiences more extreme seasonal contrasts, while the opposite hemisphere experiences milder seasonal differences, a relationship that gradually reverses over the 26,000-year precessional cycle. More dramatic changes in Earth's axial orientation have occurred over geological history. Research using high-resolution paleomagnetic records suggests that Earth experienced a significant shift in its axis approximately 84 million years ago during the late Cretaceous period. This event, characterized as true polar wander, involved a substantial 12-degree tilt in Earth's axis, potentially resulting from movements of Earth's mantle and crust relative to its liquid metal core. Such major reorientations of Earth's axis are extremely rare and occur on timescales of millions of years, contrasting with the more regular oscillations in tilt angle that occur over tens of thousands of years. These various timescales of axial variation, from the 40,000-year obliquity cycle to the 26,000-year precessional cycle to the multi-million-year true polar wander events, illustrate the dynamic nature of Earth's orientation in space across different temporal scales. Earth's axial tilt serves as the primary driver of seasonal changes across our planet, creating the rhythmic pattern of spring, summer, autumn, and winter that shapes life in the middle and high latitudes. The fundamental mechanism behind seasonality involves the consistent orientation of Earth's tilted axis as the planet orbits the sun. When the northern hemisphere is tilted toward the sun, that hemisphere receives more direct solar radiation, experiences longer daylight hours, and thus undergoes summer conditions. Simultaneously, the southern hemisphere, tilted away from the sun, receives less direct sunlight, experiences shorter days, and undergoes winter conditions. 6 months later, this relationship reverses completely as Earth moves to the opposite side of its orbit while maintaining the same axial orientation in space. The summer solstice represents the point at which a particular hemisphere reaches its maximum tilt toward the sun, receiving the most direct sunlight and experiencing the longest day of the year. This occurs around June 21st in the northern hemisphere and around December 21st in the southern hemisphere. Conversely, the winter solstice marks the maximum tilt away from the sun, producing the shortest day and longest night. Between these extremes lie the spring and autumn equinoxes, when Earth's axis is oriented perpendicular to the Sun-Earth line, producing roughly equal day and night lengths across the planet. This seasonal cycle affects temperature patterns, precipitation regimes, ecosystem functioning, and countless aspects of human activity from agriculture to energy consumption. A common misconception holds that seasons result from variations in Earth's distance from the Sun throughout its slightly elliptical orbit. While Earth's distance from the Sun does vary slightly between perihelion, closest approach occurring around January 3rd, and aphelion, furthest departure occurring around July 4th. This 3% difference in distance produces only about a 6% difference in solar radiation reaching Earth. This minor variation in solar input is far less significant than the dramatic differences in radiation distribution caused by Earth's axial tilt. In fact, the current orbital arrangement places the northern hemisphere's summer near aphelion, when Earth is furthest from the Sun, demonstrating that axial tilt overwhelmingly dominates seasonal temperature patterns rather than Earth-Sun distance. The primary driver of seasons remains the changing angle at which sunlight strikes different portions of Earth's surface throughout the year, directly determined by the planet's axial tilt. Earth's axial tilt profoundly influences global climate patterns across multiple timescales. On the annual scale, the tilt creates the familiar seasonal cycle that drives temperature and precipitation patterns worldwide. On longer geological timescales, variations in Earth's tilt angle contribute significantly to major climate shifts, including glacial interglacial cycles. When Earth's axial tilt increases toward its maximum of 24.5 degrees, seasonal contrasts intensify in both hemispheres, producing warmer summers and colder winters globally. Conversely, when the tilt decreases toward its minimum of 22.1 degrees, seasonal differences moderate, resulting in cooler summers and milder winters. These variations in seasonal intensity, particularly summer temperatures at high latitudes, play a crucial role in determining whether winter snow and ice persist year-round, potentially accumulating into extensive ice sheets over time. The relationship between axial tilt and ice ages illustrates the profound climatic influence of obliquity variations. During periods of reduced axial tilt, summer temperatures in high-latitude regions may remain cool enough to prevent complete melting of winter snow accumulation. This allows snow and ice to persist and gradually build up into large ice sheets, particularly in the northern hemisphere, where substantial land masses exist at high latitudes. As ice sheets expand, they increase Earth's albedo, reflectivity, bouncing more solar radiation back into space rather than absorbing it, which creates a positive feedback loop of additional cooling. This mechanism represents one of the primary ways that variations in Earth's axial tilt contribute to the cycling between glacial periods, ice ages, and warmer interglacial periods over geological timescales. Earth's current axial tilt of 23.44 degrees creates a climate regime that balances extremes, preventing any region from experiencing excessive heating or cooling. By distributing solar radiation unevenly between the hemispheres throughout the year, axial tilt ensures that no single region receives the full intensity of solar radiation year-round. This distribution mechanism helps moderate global temperature patterns and creates the diverse climate zones that characterize our planet. Without this tilt, Earth would lack seasons entirely, and each latitude would experience essentially the same solar conditions throughout the year. Such a scenario would likely result in extreme climatic regimes, with equatorial regions potentially becoming uninhabitably hot, while polar regions would remain permanently frozen, potentially limiting the development of the rich biodiversity that characterizes Earth today. The 23.44-degree tilt of Earth produces numerous distinctive geographical and environmental phenomena that shape our planet's physical and biological systems. One of the most dramatic effects occurs in polar regions, where the axial tilt creates the extraordinary phenomena of the midnight sun and polar night. During summer months at latitudes above the Arctic Circle or below the Antarctic Circle, the sun remains visible for 24 continuous hours on at least one day of the year, never setting below the horizon. Conversely, during winter months in these regions, the sun never rises above the horizon for at least one complete day, creating the extended darkness of polar night. These extreme variations in day length and sunlight exposure create unique environmental conditions that have shaped the adaptations of polar ecosystems. Earth's axial tilt creates a gradient of solar energy reception from the equator to the poles. The equatorial regions receive approximately 2.5 times more solar energy per unit area than the poles, with the difference largely attributable to the angle at which sunlight strikes Earth's curved surface. Due to the 23.44-degree tilt, the poles receive only about 40% of the solar energy that reaches the equator. This energy gradient establishes the fundamental temperature differential that drives global atmospheric and oceanic circulation patterns. The uneven heating between equatorial and polar regions creates pressure differences that generate prevailing wind patterns, ocean currents, and weather systems that distribute heat around the planet, moderating temperature extremes and creating Earth's complex climate system. The existence of distinct climate zones and biomes across Earth's surface largely stems from the planet's axial tilt. Without this tilt, each latitude would experience essentially the same solar conditions year-round, likely creating uniform bands of climate from equator to poles with little seasonal variation. Instead, Earth's tilt creates the complex mosaic of tropical, temperate, and polar zones, each with distinctive seasonal patterns that support diverse ecological communities. The intermediate tilt of 23.44 degrees strikes a balance that has proven remarkably conducive to life. If Earth's tilt were significantly greater, seasonal extremes would intensify, potentially creating inhospitable conditions across much of the planet. Conversely, a much smaller tilt would reduce seasonal variation, potentially limiting the diversity of ecological niches available for life to exploit. Earth's axial tilt of 23.44 degrees falls within a moderate range compared to other planets in our solar system, which display a remarkable diversity of axial orientations. Mercury, with its minimal tilt of just 0.03 degrees, essentially has no seasons, while Venus has a modest tilt of 2.64 degrees, but rotates retrograde, opposite to most planets. Mars possesses a tilt, 25.19 degrees, quite similar to Earth's, resulting in comparable seasonal patterns despite its greater distance from the Sun. The gas giants show dramatic variation. Jupiter maintains a relatively small tilt of 3.13 degrees, while Saturn exhibits a substantial tilt of 26.73 degrees, creating notable seasonal effects despite its great distance from the Sun. Uranus presents the most extreme case with an axial tilt of 82.23 degrees, essentially rotating on its side relative to its orbital plane, creating extraordinarily long and extreme seasons. This comparative analysis reveals that Earth's axial tilt occupies a Goldilocks zone that supports relatively moderate seasonal variations compared to some other planets. Our moderate tilt creates sufficient seasonal contrast to drive dynamic ecological processes without producing the extreme conditions found on planets with very large axial tilts. The relative stability of Earth's axial tilt over time also contrasts with Mars, whose tilt is believed to have varied much more dramatically over its history due to the absence of a large stabilizing moon. These comparisons highlight how Earth's particular axial characteristics contribute to its habitability, as both the angle of tilt and its stability over time have helped create conditions conducive to the development of complex life. The moon plays a crucial role in stabilizing Earth's axial tilt, preventing the wild oscillations that might otherwise occur due to gravitational influences from other planets, particularly Jupiter. Without the moon's stabilizing presence, Earth's axial tilt might vary much more dramatically over time, potentially creating extreme climate fluctuations that could pose significant challenges for the development and maintenance of complex life. Computer simulations suggest that without the moon, Earth's axial tilt could vary by as much as 85 degrees over time, potentially flipping the planet nearly onto its side and back again over geological timescales. This stabilizing influence represents one of the moon's most significant contributions to Earth's habitability, maintaining the relatively narrow range of axial variation that has helped create Earth's long-term climate stability. Earth's axial tilt represents just one component of a complex set of astronomical parameters that collectively influence our planet's climate over long timescales. These parameters interact in a system known as the Milankovitch cycles, named after Serbian geophysicist Milutin Milankovic, who calculated their combined effects on Earth's climate in the early 20th century. Three primary components comprise these cycles: variations in Earth's orbital eccentricity, precession, and obliquity. Each of these parameters cycles over different time periods, approximately 100,000 years for eccentricity, 26,000 years for precession, and 40,000 years for obliquity, creating a complex pattern of overlapping astronomical influences on Earth's climate. The interaction between axial tilt and other orbital parameters creates particularly significant climate effects. For example, precession determines which hemisphere faces the Sun during perihelion versus aphelion. Currently, Earth reaches perihelion around January 3rd, meaning the southern hemisphere experiences summer when Earth is closest to the Sun, while the northern hemisphere has summer when Earth is furthest from the Sun. This arrangement moderates seasonal extremes in the northern hemisphere, while amplifying them slightly in the southern hemisphere. Over the 26,000-year precessional cycle, this relationship gradually reverses, altering the intensity of seasons in each hemisphere. When variations in axial tilt and orbital eccentricity align in particular ways, their combined effects can either amplify or diminish seasonal contrasts, potentially triggering significant climate transitions. These astronomical cycles have significantly influenced Earth's climate history, particularly the glacial-interglacial cycles of the past 2 million years. Paleoclimate records show clear correlations between Milankovitch cycle parameters and major climate shifts, with variations in axial tilt playing a particularly important role in triggering transitions between glacial and interglacial periods. The 40,000-year obliquity cycle correlates strongly with climate oscillations in the earlier part of the Pleistocene epoch, highlighting the significant influence of axial tilt on global climate. In more recent climate history, the 100,000-year eccentricity cycle has dominated climate oscillations, but axial tilt variations continue to play an important modulatory role. These complex astronomical influences on Earth's climate demonstrate how our planet's orientation in space, including its axial tilt, has profound implications for environmental conditions at the surface. Earth's axial tilt of 23.44 degrees represents a fundamental astronomical characteristic that shapes countless aspects of our planet's physical and biological systems. From the seasonal cycle that drives weather patterns and ecological processes to the long-term climate variations that have influenced evolutionary trajectories, this modest tilt of our planet's rotational axis relative to its orbital plane creates profound and far-reaching effects. The historical progression of understanding Earth's axial tilt reflects humanity's broader journey of astronomical discovery, from ancient shadow measurements to modern precision calculations that can detect even subtle changes in our planet's orientation. This knowledge reveals Earth not as a static object in space, but as a dynamically oriented planet whose axial characteristics have evolved over geological time and continue to change gradually through astronomical influences. The comparative stability of Earth's axial tilt, maintained within a relatively narrow range of 22.1 to 24.5 degrees over a 40,000-year cycle, has provided crucial environmental consistency for the development of complex life. Unlike some other planets with extreme or highly variable axial orientations, Earth's moderate and stable tilt has helped create the Goldilocks conditions that support our planet's remarkable biodiversity. The Moon's stabilizing influence on Earth's axis represents one of several astronomical factors that have contributed to Earth's long-term habitability. As we continue to explore other planets and solar systems, understanding the role of axial tilt in planetary climate and habitability provides important context for assessing the potential for life beyond Earth. Earth's particular axial characteristics remind us how fundamental astronomical parameters shape the conditions for life on our planet and potentially throughout the universe.